So today we are going to move towards we're going to continue with the non-equilibrium dynamics part once again. And yeah, so here's a brief overview of the things which we covered in the last 3 lectures. So I'm just going to skip it, assuming that those of you who are present here today were present yesterday as well. Okay, so today what we are going to start with is basically something called the surface directed spinodal decomposition. Okay, so this is something which I already mentioned one day before. So today, yeah, so we are going to basically look at it in a greater detail today. And then with that, finally, we'll move on to another example, which is mainly these colloidal particles here. So the surface properties because of the colloidal particles. All right. So what do we mean by this surface directed spinodal decomposition? So if you remember, like I told you one day, that we already knew that we already talked about the phase diagram of a normal chemical system, and we learned the concept of critical temperature. So we know that when the fluid is above the critical temperature, it's in the homogeneous phase, and when you have it below the critical temperature, it's in the two-phase demixed region. So here in this picture here, what I show you is basically a schematic of 2 surfaces, which are, and in between the 2 surfaces, you have a binary liquid mixture, which is basically kept confined in between the 2. And so say, for example, these walls, we specify the coordinate as z equal to 0 and z equal to d, capital D. And basically what you have to do next is to quench the temperature of the fluid. And under such situations, like we saw before, that you have some kind of structures which are forming in this intermediate fluid. And this phenomenon is a non-equilibrium phenomenon. So it's a time-dependent properties which one is interested in. And it's known as this surface-directed spinodal decomposition. Yeah. So now the question is, how can you do the modeling of such systems? Yeah. So if you want to understand the time-dependent properties of such systems, what is the way to go forward? Okay. So now, if you think about it, so if you want to look at the free energy of the whole system, basically the fluid, you can divide it into 3 parts. Yeah. One part will be purely the bulk contribution, like the bulk free energy. And the bulk free energy corresponds to the part which is basically the free energy part which you obtain when you don't have any kind of surfaces and there is no surface effects, which means it corresponds to the periodic boundary condition, etc. Now, in addition to the bulk free energy, you will have contributions because of the 2 surfaces. That's what is captured in this Fs1, say the surface at z equal to 0 and the second surface, say at z equal to d. Now, the idea is the following, yeah. So you have the free energy contribution, which is coming from these 3 different parts. What you can do now is to write down the expressions of these different free energy contributions. Now, for the bulk free energy, typically what is done in the literature is one basically characterizes the bulk free energy in terms of something called the Ginzburg-Landau free energy functional. And so what happens in the Ginzburg free, so by the way, so this Ginzburg-Landau free energy functional, if you remember, I explained it on the very first day, where you remember I showed the schematic picture of this free energy functional. How does the function look like? How does the properties change as a function of temperature, etc. Yeah. So it's the same functional basically. You have a squared term, 4th order term, and the gradient term. Now, the gradient term basically takes care of the interface formation. And why does the gradient occur? Because remember, whenever you have domains forming, yeah, or whenever you have interfaces, the value of the order parameter on both sides of this domain going to be different. So it's going to lead to some kind of gradient in the order parameter. Okay, and the square term and the 4th term, so the psi square and psi 4, they basically take care of this phase transition. Yeah, so that's like the usual Landau free energy. In addition, you have the square gradient term, which is due to Ginzburg, and that takes care of the interface formation and thus the phase separation. So this is the usual process in which the bulk free energy part is characterized. Now, what about the surface free energy? Yeah? So there are different methods of considering the surface contribution. Just like the bulk free energy, one can also write down similar expressions for the surface contribution as well, where you will have the surface potential, which will enter into the surface free energy. What do I mean by the surface potential? So you have the surface and you have the fluid molecules. There will be an interaction between the surface and the fluid molecules. So that's what is the potential, yeah, the surface potential. So one can include that surface potential into the properly into the surface free energy contribution as well. Another way to do that is through the boundary conditions, and that's what is mentioned here in this expression. So this corresponds to the surface free energy, where the alpha and the H, these two terms actually take care of the surface preferences. Okay, so they will determine which of the two phases of the intermediate fluid will come and sit on top of the surface. Now, how do you understand that? Okay, so let's try to understand it in a simplest hand waving way. So let's say that, okay, let's consider just the, let's consider only the second term, okay? Let's forget the first term for the time being. Let's consider only the H times psi ds term. Now, you know that when the system actually is trying to, when it's undergoing the non-equilibrium, the Spinodal decomposition process, it's basically trying to lower the free energy, the total free energy of the system, right? And in order to decrease the free energy, the surface contribution will also have to decrease, which means that if I consider this term, H times integral of psi ds, it should become negative for it to be minimum, right? For it to minimize. Now, if H times psi ds, it has to be negative. And for example, say I set H to be positive, what does it mean? The psi has to be negative, right? So that actually tells you that if I put H positive, it's basically the phase which corresponds to psi negative, which let's call the B phase, will come and form on top of that surface. So this way, by tuning the value of H, tuning the sign of H, you can actually control which of the two phases will come and sit on top of the surface. Okay, so that's how these the parameters H and alpha similarly will determine the layer which is forming on top of the surface. Okay, and it will also determine the strength of this order parameter on top of the surface as well. For example, if I take a higher value of H, the value of psi is going to be different than if I take a lower value of H. Okay, so this is the basic way in which one can, the general methodology with which one typically deals with the, this kind of non-equilibrium process. And the idea is the following. So you start with an initially homogeneous system, which is at a very high temperature. That's why it's initially homogeneous. Then you quench it below the critical temperature, and you want to see what is happening as a function of time during this non-equilibrium process. Okay. So this is one way of doing such things. It's also called the Ginzburg-Landau free energy functional method, the Kahn-Hilliard kind of method. So let me now just show you some of the results, okay, which will be more interesting for you. If you are interested in the methodology part, please let me know. I'll send you very good some scholarly articles, papers, or books in which you can look into it detail. But for the time being, let's just have a look at the properties, the results here. What happens during these SDSD, surface-directed spinodal decomposition? All right. So in the first picture, I show you the snapshots during this non-equilibrium process as a function of time. So it starts from, show the pictures time t equal to 80, 800, etc. So what you see here, okay, by the way, now in this picture, this top surface and the bottom surface, both of them prefer the A type of particles, which are marked by the black color, okay? So the gray color corresponds to the B type of particles and the black color to the A type of particles. And what you see here is the following. Initially, you see that it's more or less still like homogeneous. There is not really very prominent layering which are formed yet. As time progresses, you see it's gradually the layers are developing. Yeah. For example, at t equal to 800, see if you look at the top surface, it has now already got more number of A particles. So it's trying to form a layer of A particles. In the intermediate region, you see some kind of domains of some kind of structures are going on, they're forming. Yeah. Similar thing is happening at the bottom surface also, because the bottom surface also prefers the black particles, but you don't really see it because the thickness of that layer is not thick enough for you to see it now. Let's now go ahead at time t equal to 1600. You see at 1600, you have a very visible layer of A particles on top of the top surface and also at the bottom surface. And in the intermediate regime, these domains which are forming, now they have become very large. Yeah. So if I can compare these intermediate domains, say at t equal to 80 and t equal to 1600, clearly you see the domains have become much larger now. Okay. Similarly, now if we move on to the next time, say t equal to 8000, now at this time, I have a very prominent layer of A type of particles, namely the black particles, which are formed on top of the top surface as well as both the bottom surface. And the domains have really now become way bigger, right? So it's almost now going towards the steady state kind of situation, moving towards it. So this is the 3D view of the situations which are happening. Let's now try to look at the snapshots in the slices, okay? So in the second picture, this column here, this is the slice from the side view, basically, okay? So you have this 3D picture, you are looking at it from the side. So it's mainly in the XZ plane. Huh? So you see that at time t equal to 80, at early time, there's not really, there is some kind of structure which is going on in the intermediate fluid, but there's not any prominent layering which is still has formed. At 800, it has now started forming. 1600, it's getting thicker and thicker. And at the same time, in the vertical direction, you have these domains are now getting much more bigger. Finally, at 800, you clearly see that you have very prominent layers of A particles which have now formed on top of both the top surface as well as the bottom surface. Okay. Now let's try to understand what's happening if I consider the slice in the horizontal plane. Okay. So this picture here, the next picture, it actually shows the snapshots in the mid plane of this system. Okay. So you have this cubic system, you just look at it in the XY plane in the Z equal to d by 2 in the midsection. Okay. And now here what you see is basically that at initial time you have some kind of domains which are forming, but they're very small. So it's more or less still like homogeneously mixed. Gradually these domains are forming, they're getting bigger and bigger. And yeah, so finally you have these domains of both A and B type of particles which are forming in the sliced-like way. So this is the basic mechanism which goes on during this SDSD process. And now let's try to figure out how to quantify this kind of non-equilibrium phenomenon. Okay. So in order to quantify that, one way to look at it is through the layer-wise defined order parameter. Okay, so it's in the first picture. So this is the order parameter, and the definition of this order parameter is going to be the same that I mentioned yesterday as well. Yeah, if you remember when I was explaining those the non-equilibrium properties of those the confined fluid, I told that the moment you have a surfaces, you have to define the order parameter as the local order parameter, and it's the same order parameter which is being plotted here. So initially, what you have is there is a surface adsorption layer which gets prominent because you have this positive value of the order parameter. Okay. Next to one surface adsorption layer, you have a depletion layer where the order parameter is negative. And then finally in the middle, it's you basically have this almost a bit, yeah, one depletion layer, and then finally you have the symmetric kind of profile, and you have another surface adsorption layer which is forming close to the second wall. And as time progresses, the thickness of this depletion layer increases, and then finally in the middle you have this kind of profile where in the middle, so you have one adsorption layer here, one depletion layer, and in the middle basically these two layers are merging on top of each other. Now another way to quantify it is to look at the correlation function. Okay, so the correlation function is defined in this expression here. What we do here is that this correlation function is calculated in the XY plane. Okay, so you are looking at it for a constant value of Z. Okay, so you basically take a slice along the xy direction, and this in the xy plane, you are looking at the correlations of these particles at different times. Okay, all right. So this correlation function will basically also give you the same kind of message that as the time progresses, you have these the layers which are getting thicker and thicker. So yeah, so basically where you have the maximum of these correlations, that corresponds to those layers, and the minimum, they correspond to the depletion layers. Okay, so these are some of the basic properties of this kind of surface directed the spinodal decomposition phenomenon. And this is something now we would like to be interested in looking at for a very interesting topic, which is mainly this hot particles or the hot Janus particles which are suspended in a solvent. Okay, and if you remember, this is an example of confined fluids which I mentioned during the first lecture on the very first day. And just to mention it once again here, so this kind of particles, so basically these Janus particles which are being laser heated by some kind of being laser heated with sufficient intensity, and in such situations they're seen to undergo some kind of active motion, and you observe the formation of this kind of asymmetric structure around the particle. So this is basically a very hot topic in the scientific community at the moment all over the world, and there is huge number of work which is going on. So this is something which might be you might be interested in if you want to learn about the recent works which are going on in the direction of confined fluids. So I'll just explain in 1 minute what's the specific properties of this system. Okay. So what scientists do is the following. Okay, you take a colloidal particle, okay, which is mainly of nanometer size, and you coat this colloidal particle with two different materials on both sides. Okay, and when you are coating these particles with materials of different size, it basically attains different surface properties on both sides. So that's what's shown here in the schematic picture here. You have this spherical colloidal particle whose right side, which is basically coated with gold, it has a different surface property than the left hemisphere. Okay, and this right hemisphere, it's also called cap. So this is a terminology which is used hugely in the literature of active particles. So the cap basically refers to the part of the colloidal particle which you are coating with a certain material in order to achieve certain functional properties or surface properties. So in this particular situation, we are coating it with gold. What it means is that now if I take this Janus particle and I put it into the solvent, so remember that the solvent is once again a binary solvent, which is close to a phase transition, second order phase transition. So I have two glass slabs here, one top slab and a bottom slab. I have the binary fluid in between, and I have the colloidal particle, which is kept here. Now you shine laser on top of this system, okay, from the top. And you choose the wavelength of this laser in such a way that the right part of this fluid, of this colloid, which is basically called the cap, this cap now absorbs the light, okay? But the left hemisphere of the colloid and the fluid, they don't absorb the light. And why don't they? It has to do with the wavelength, okay? So you have to match it in such a way that basically the cap absorbs the light. So what happens then? The cap will absorb the light, it will get heated up, okay? And this heat will then propagate from the cap part into the solvent as well as into the left part of the colloid, right? So that's just because of pure heat conduction, okay? And when the heat is propagating, so now you have a temperature gradient which is developing in the system, right? So clearly, the part of the fluid which is close to the cap, there the temperature will be much higher because it's the hottest here. And as you go farther and farther away from the cap part, the temperature is going to be lower there. Okay, so you have a temperature gradient which has now developed in the system. It's a local gradient. And what is also interesting, if you think about it, this gradient is also time-dependent gradient, right? Because you have the heat which is basically conducting. So this temperature profiles are propagating from the colloidal, right? So you have a time-dependent local temperature gradient, okay? And what is observed in experiments and as well as in computer simulations is that If you do this same kind of colloidal particle and you shine the light, etc., under certain situations, you see that this particle now undergoes active motion. Okay, so it just starts to move suddenly and it moves in a certain direction. And that is something which is known as the active motion. Why is it active? Because the particle itself does something itself, okay, because of which it now starts to move. So there is some kind of activity which it is developing itself. Okay. Now, what you also observe, another interesting thing is that if you look at the fluid surrounding the Janus particle, so in this picture here marked by D, what you see is an asymmetric structure which is formed around the particle. Okay. And the question is, of course, why does this asymmetric structure now develop around the Janus particle? Okay, so that is something that's a question of very much of scientific interest to the this confined fluid community. Okay, so I'll spend the last couple of slides today trying to explain to you this work in a bit detail, because I thought it will be useful for you, because this is something which, like I mentioned to you once again, that it's something, it's a very active topic at the moment. So maybe it's better if I explain it to you in a bit detail so that you might, find it a bit interesting and you know what kind of research is going on at the moment. All right, so the questions which we are going to address now in the couple of next slides are the following. First of all, what is the mechanism behind the motion of this colloidal particle? Okay, what is the mechanism behind the formation of this kind of asymmetric structure around the particle? In principle, say in particular, this asymmetry which you see here, which has formed around the particle, is it purely because of the Janus nature of the colloidal particle, or there is something else? Okay, so we will see that. Why is it asymmetric at all? And then the third question is, of course, why is it important in the broader sense? What kind of applications do this kind of particles have? Okay, so those are some of the questions which we are going to address today. And before I move on, let me just try to show you one video basically from the experiment, which shows how this active particle moves. Yeah, so let me just try to, let's see if it works out, okay? If it works, it's fine. Okay. All right, so I hope you can see the movie. I hope I have shared the screen properly. So what you will see here, so it's basically a Janus particle, okay, where you have the cap here, and you are doing the same experiment where you're taking this particle, you have put it in a binary fluid, which is close to the critical point, and then you are shining laser on top of it. And as you will see, you will first see some kind of layers which are developing around this Janus particle, okay? And then you will see how the particle moves, basically. Okay, so like you see, the particle has, so yeah, you see it has started moving. And if you noticed carefully, I hope you have seen that it also changed the direction of the motion. Yeah. So initially, if you start, the particle starts to move this direction. You have layers which are forming. Then it changes the direction. Okay. And it starts to move in the upward direction. And you clearly see a very asymmetric structure has now formed around the particle. And this layer which is formed, it gets thicker and thicker with time, and the particle undergoes the motion. Okay. All right. So now the question is, once again, what is the mechanism behind the formation of this kind of asymmetric structure, and what is the reason behind the motion of this particle? Okay. All right. So let's now move on to the theoretical modeling of this kind of system. So since we are now going to do some kind of theoretical modeling, let me just try to tell you what is the basic analogy behind this experiment that you observe here and the modeling that we are going to do. So first of all, one difference which you should keep in mind is that if you remember my earlier slides where I was explaining to you the critical point, I talked about this kind of an upper critical point, yeah, where the binodal line was upside, yeah, which means that when you are above the critical temperature, the system is in the homogeneous phase, and when you are below the critical temperature, it's in the demixed state. Okay, whereas this experimental fluid, which is considered in the experiments that I showed you, it has a lower critical point. What do I mean by lower critical point? Means that the binodal is basically upside down, which means that when the fluid is at a temperature which is lower than the critical temperature, it's homogeneously mixed, whereas if it is at a higher temperature, then it's in the demixed state. So it's basically just the opposite. Okay. And what is the advantage of that in case of experiment? What is the reason? Why do the experimentalists suddenly take this kind of a lower critical point? Well, the reason is the following. If you take this particular fluid, it's called water lutein mixture. So that particular fluid has a lower critical point, Cp, which is marked here. And this temperature is very close to the room temperature. It's close to 35 degrees centigrade. Okay. What it means is that when you take this fluid and just put it at room temperature, the fluid is homogeneously mixed. There is nothing, no phase separation, no structure formation, nothing which is happening. It's very much homogeneously mixed. Now you take the colloid and you put it in this fluid and you heat up. So when you shine the laser, as you understood, some part of the fluid will get heated up, right? Because of the heat conduction. And it might so happen that if this fluid gets heated up, that part of the fluid will then, the temperature will then actually increase and it will enter into this two-phase demixing region, which means that that part of the fluid where the temperature has now increased, that part will then try to undergo some kind of spinodal-like phase separation or like, surface-directed spinodal decomposition. Okay, so that's the main advantage. Now, in case of taking up this kind of a lower critical point, say for example, in principle, one can of course start in experiments as well with an upper critical point as well. But the problem there is that maintaining the temperature of a fluid at such a high temperature is pretty difficult technically in the experiments. Okay, so it's much easier when you have a fluid with a lower critical point, whose lower critical point is also close to the room temperature. Things are much more easier to be controlled in a precise way. So that's the reason in the experiment you have a lower critical point, whereas in case of the theoretical modeling, we're going to consider an upper critical point. Okay. So say to explain it in other words, in the experiment, when you shine the laser and you heat up the colloid or heat up the fluid, in the theoretical modeling, we are actually going to cool the fluid. We are going to do a temperature quench. Okay. Now, what about the surface properties? So like you saw, these layers which are forming, okay, they correspond to some kind of wetting property, right? So either the particle is hydrophobic, which means it doesn't like the water phase, or it's hydrophilic, which means that it likes the water phase to come and form a layer on top of the particle. Those properties are taken into account once again by in terms of the surface free energy. Okay, the same kind of modeling which I was explained to you before today and yesterday as well. Okay, so those things will be taken care of by appropriate modeling in terms of the free energy functional. All right, so I hope the analogy is clear now, and with that, then let's try to move on to the theoretical modeling and some of the results. Yeah, so what is actually happening in this kind of system? Okay, so I'll spend a few minutes trying to explain the theoretical modeling. So as you already see now, in this kind of system, we have two different fields, right? Two time-dependent fields. One is the temperature field, another is the order parameter field. And these two fields are coupled with each other, right? And both these fields are time-dependent. So after you turn on the laser, or say after you do the temperature quench, you have a temperature gradient which is developing in the fluid. And this temperature gradient is changing with time. So it's a time-dependent temperature field. And depending on the local temperature, the order parameter value is also going to change, right? So you have an order parameter field as well. It depends on the space coordinate. And that order parameter depends on time as well. So the temperature field and the order parameter field are now coupled with each other. Okay, and the question is, how do we solve those two fields as a function of time? Now, in order to do that, for the temperature field, as the simplest approximation, what one does is to solve the heat diffusion equation. So the heat diffusion equation, like you know, I mean, it's basically takes care of the fact that you have a temperature source and you have the temperature field, and how does it changing as a function of time and space. So that's what is shown here. Don't worry about this constant term d here. It actually refers to the ratio of thermal conductivity and mutual diffusivity, but don't worry about that. Just for the time being, I mean, you know, just keep in mind it's some kind of constant, okay? So you're actually solving the heat diffusion equation to see how the temperature changes as a function of time. What about the order parameter field? Well, it's the same kind of phenomenology which I explained to you before. You start with the Ginzburg-Landau free energy functional, where you have a psi squared term, psi fourth term, as well as a square gradient term. Now, in this kind of a system, in a binary fluid, the total order parameter is conserved. So if you have an order parameter conservation, you have a current in the system, right? So that's the continuity equation, which you must have learned in your statistical mechanics course in your MSc courses, yeah? So there is some kind of continuity equation where you can express the time dependence of the order parameter with the concentration current. So the J is the concentration current, which is related to the chemical potential, mu, and mobility of the fluid. Okay, and then if you do a few steps of algebra, you can show that the time dependence of the order parameter del psi del t can be written in terms of the free energy functional F. So now if I know the terms which are appearing in the free energy functional, I can very easily calculate the derivative, which is there in the on the right hand side. And then from there, I can get the time dependence of the order parameter. Okay, it's as simple as that. Now, one trick is here, which is that if you look at this free energy functional, this a psi square plus mu psi 4, etc., usually this is in the literature, usually this is done for an isothermal system. What do I mean by isothermal? Means if you look at the fluid, everywhere in the fluid, temperature is the same. Okay. So the term A here, the constant term A here, that is actually related to the temperature, and that is constant for the fluid. Everywhere in the fluid, it's constant. Whereas in this type of system, like you see, we have a temperature gradient. Yeah. So the temperature is once again a function of the space coordinate. It's a field. How am I going to take that into account? One way to do that is to replace this constant term A by the temperature field. Okay. And that's what is done here in this expression. You need to do some kind of tweaking, some kind of, some sort of tricks you need to use in order to replace the A by the temperature field. I'm not going to get into the details of those tricks, but just keep in mind that this constant temperature, the constant term A here is going to be replaced by the reduced temperature field, T tilde, okay? And that's how basically the temperature field now gets coupled to the order parameter field. So if you do the few steps of algebra, you will finally arrive at this expression, which is given within this yellow border here. So on the left-hand side, you have del psi del t, which tells you how the order parameter is going to change as a function of time. On the right-hand side, you see within the Laplacian, you have this first term where the temperature field is now coupled to the order parameter field. It's a product term, yeah? And in addition, you have the other usual terms, which is basically psi cube and the Laplacian. And how do you get these two terms? Well, starting with this free energy functional, if you just take the derivative, so you have to take del f del psi. If you take del f del psi, the psi square term will give you psi. That's why you have a psi here. Psi to the power 4 will give you psi cube. You have psi cube here. And the square gradient term will give you the Laplacian. Okay, so that's how you obtain these three terms. And in addition to it, you need to add a noise term because you have a system which is close to the critical temperature and you have thermal fluctuations. So one needs to add certain kind of white noise as well. So this is the basic this is the basic methodology. Okay, we are now going to solve these two equations. We have the heat diffusion equation, solving which will give us the properties of the temperature field. And we have this Cahn-Hilliard-Cook, the modified CH3 equation, which is marked within this yellow box here. If you solve this equation, you are going to get the properties of the order parameter field. And the temperature field and the order parameter field are getting coupled by the first term, which is appearing into this equation here. Okay, so that's what we're now going to do. And you will have to implement certain boundary conditions, which will take care of the wetting properties of the colloid. So if you do that properly, what you are going to observe is the following. So first I show you the properties of the temperature profile. Okay. So you have to solve the heat diffusion equation subjected to certain boundary conditions. And if you solve it, finally, you will arrive at this first equation here, okay, within this blue, the blue box, basically. So if you look at this equation, you see that on the right-hand side, I have an exponential term. So it's exponential minus something times time. What does it mean? It means that when the time is very late, if I'm going to the limit t tending to infinity, this exponential term will drop down, right? So it's exponential minus infinity. So this will basically drop down the right-hand side. What I will have is the temperature is equal to T1 everywhere in the system. What it means is that now in the steady state, I have reached the situation where everywhere in the fluid, the temperature it has attained is basically the temperature of the cap. Okay, so it has reached that temperature everywhere. The heat has propagated completely. And that's what you see here. So just focus on the black data and the blue data. Okay. The left-hand part here, this yellow marked region, that corresponds to the cap part of the colloid. Okay. So initially, the cap part, the colloid has a temperature -1 and the fluid has a temperature +1. So you have a strong gradient in the fluid. Then as time progresses, you have this heat diffusion, etc. going on. And finally, you see at a very late time t equal to 200, everywhere in the fluid, the temperature has reached a value which is almost close to the cap temperature -1. Okay? And this is exactly what is predicted by this analytical expression here. And that's what you captured in the computer simulation. Okay, so this is what is happening to the temperature field. So now let's try to see what is happening to the order parameter field. Okay, so if you look at the order parameter field, you're going to see some kind of structure formation. And that's what you see in this color, the beautiful color picture here. So time t equal to 0, by the way, this gray circle here, so that corresponds to the colloid. So these are the results first for the homogeneous colloid. It's not Janus, it's for homogeneous colloid. And I'm looking at slices, okay? So you see that at very early time, t equal to 0, the initial time, the fluid is homogeneously mixed. And the different colors here correspond to different values of the order parameter. Only positive value of the order parameter, only one phase, which is the A phase, is shown here, okay? So the white part in the picture, that corresponds to the B phase, which is not plotted. Now you see as time progresses, you have certain layers of the A particles which are forming, okay? So on top of the colloid, you see there is a layer forming with a very high value of the order parameter, close to 1.2. And that's because the colloid prefers the A type of particles. So the A type of particles are coming and forming a circular layer around the colloidal particle. Next to one layer of the A particles, you have a white layer. What does it mean? It means you have a depletion layer which consists of the B type of particles. So you have one layer of A particles. Next to it, you have another layer of B particles. Then another layer of A, another B. So the A and B, they just keep alternating. Yeah, they just keep repeating. And farther away from the colloid, you have spinodal-like phase separation, the usual domains forming, which you see very far away from the colloid. Okay, and this thing goes on as time progresses. You have the layers which are getting thicker and thicker. If you look at the value of the order parameter, that is increasing. Like you see here, if I compare between 100 and 200, the red part has now become much more thicker. So the order parameter is increasing. The layers are increasing in numbers. And finally, you see that equal to 300, it's like the layers have now spanned over the entire simulation box. Okay. And after that, something very interesting happens. Now the layers actually start to break up, like you see at t equal to 400. And then finally, in the steady state, you will have a situation where the colloidal particle is basically trapped at the interface between the A and B type of particles. So this is something called the trapping of colloidal particles. It's called trapping at interfaces, which is once again a very interesting topic itself in the field of confined fluids. Okay. All right. So this is the basic thing which is going on here, that you have layers of A and B type of particles which are forming and they are getting thicker and thicker. Okay. Now, to characterize this, one looks at the order parameter profile. Okay. So the psi of R as a function of the distance from the colloidal surface. Yeah. So let's have a look at the initial time first, time t equal to 2. What do you see? Very close to the colloid at r equal to 1. So r equal to 1 refers to the time which is very like, just close to the colloid surface basically. You see that you have a layer, one surface adsorption layer, which is formed on top of the particle. The order parameter is positive. Yeah. And then you have a small depletion layer here. And then almost everywhere in the fluid, the order parameter is close to its initial value. There's not really much what is happening. Okay. So that's because you have, it's just the initial time and you have only one layer which is formed and not much is happening, in the rest of the fluid. Now, as time progresses, at a very late time, you see at the late time, you have so many oscillations which have now formed. So you have multiple maxima and minima now. Why is that? Because you have now many layers which have already formed in the fluid. So every peak here corresponds to each layer which is formed around the colloidal particle. Okay. So this snapshot which you see here is actually getting reflected in terms of this order parameter profile very nicely. One can also look at the correlation function. Okay, so like I was showing you the properties of correlation function before. One can look at the correlation function here as well. And what you expect to see is the similar thing, that at very early time, the black data, you see there is only one peak here and one minima because you have only one surface adsorption layer and one depletion layer. Whereas if you look at very late time, for example, say the blue data, you have multiple peaks there, yeah, because you have these the oscillations or different layers which have formed. Okay, so these are the results for a homogeneous colloid. Okay, when you have turned on the laser, and so you have the Spinodal like decomposition which is going on around the colloidal particle. Now let's look at a situation. Okay, so this is more or less the same, so I'll just skip it. Now let's have a look at the situation where you have a Janus particle. Okay, so the right part of the this spherical colloid here, so the yellow part, that corresponds to the cap part, and the cap part absorbs the light. Okay, now starting from time t equal to 0 to t equal to 400, we don't turn on laser at all. So from t equal to 0 to 400, whatever is happening is purely because of surface adsorption, surface enrichment phenomena. There is no temperature gradient in the system. It's constant temperature. And what you see is that starting from an initially homogeneously mixed state, so at t equal to 0, you clearly see the homogeneously mixed phase. Then as time progresses, you have a surface adsorption layer forming on top of the colloid. Yeah, you have a thin blue layer which is formed on top of the particle. And you have these domains which are forming, and these domains will get bigger and bigger. Finally, in the steady state at equal to 400, you have this surface adsorption layer which is formed on top of the particle. So this the layer which you observe at equal to 400, this has formed purely because of surface enrichment phenomena. There is no temperature gradient at all till now. Okay. Now say at t equal to 401, now I turn on the laser. So from t equal to 400 onwards, whatever is going on, that phenomena is going to be in the presence of surface effect as well as temperature gradient. So there are two things which are now going to be important. And there clearly you see that if you wait for a long time at t equal to 400 at a very late time, you see a very asymmetric structure formed around the particle. If you compare the steady state profiles at t equal to 400 and 1400, there is no doubt the profile, the structure which is formed in the presence of a temperature gradient is highly asymmetric as compared to the one at t equal to 400. What does it say? Well, what it tells is the following, that when you have a temperature gradient, the asymmetry of the structure gets more and more enhanced. Okay, and this happens due to something called the Sorey effect. So it has to do with the presence of some kind of temperature gradient in the fluid. So clearly you see that if you have a fluid which is isothermal, the properties which you see there are very different from a fluid which has a temperature gradient. So the moment you have a temperature gradient and you have surface effects, things become extremely complicated and very interesting. Okay. All right. So if you remember in one of the introductory slides, I raised the question that this asymmetry in the structure, which you see, this kind of asymmetry, is it only because of the fact that the colloidal particle is Janus, or there is something else? And the answer is clearly that it is highly asymmetric because of the presence of an temperature gradient. Okay. All right. So this was for a Janus colloidal particle, which is kept in the in the fluid. Now let's try to confine this particle. And what do I mean by confinement? So I have two glass slabs, okay, top one and the bottom one, and I arrange the distance between these two slabs in such a way that the distance in between the two slabs is almost of the order of the colloid diameter, so that the colloidal particle is almost like confined there. Okay, it can't really move, it's fixed. And in that situation, we do the same kind of quenching experiment, or in other words, we do the same kind of laser heating experiment. What do you see then? So what you see here is the following. First of all, we are going to consider the situation here. We are going to compare in between two situations. In one case, when you have a thin film, and the other case, when you have a thick film. Let's start with the thin film first. Okay. So in case of the thin film, you see that at early time, you have some surface absorption layers which are forming on top of the glass slabs, both the glass slabs. And the glass slabs and the colloid, they prefer the same component of the fluid. Okay, let's say the A type of particles. Okay. So you see the grit layers are forming on top of the colloid as well as the two slabs. And in the middle of the fluid, you have some kind of structures which are forming, some kind of domains are forming. As time progresses, this layer gets thicker and thicker. If you look at the value of the order parameter in the layers, they will get higher and higher until finally you have a liquid bridge which is formed, which has actually covered the colloidal particle and the surfaces completely. So this is called bridge formation. Okay. Now, if you compare this situation to the case of a thick film, the thick film is the situation which is shown here on the right-hand panel. The basic mechanism is the same, right? So here also you have some kind of structure which is layers which are forming on top of the colloidal particle, layers which are forming on top of the glass slabs, and then you have Spinodal-like decomposition which is going on in the fluid, in the intermediate fluid. But the interesting difference to note here is that in case of thick film, even if you wait for a long time, there is no bridge formation which is occurring around the particle, which is actually connecting both the slabs as well as the colloid. No, there is no bridge formation which is happening in case of a thick film. And this is something extremely important. Why? Because say if I take a thin film, the left-hand side picture, if I take this thin film and I put another colloidal particle next to the first one, because you have this colloid bridge, the liquid bridge which has formed, simply because of capillary interaction, you will have the second colloidal particle which will get attracted to the first one, and you will have an assembly of colloidal particles which will form. But in case of a thick film, such situation will not occur. So it has very important consequences and applications. Okay. All right. So now let's talk about the motion of the colloidal particles. You remember that video that I showed you in the experiment. So you saw that after I turn on the laser, the particle it starts to move in one direction, then it changes the direction. You have this, the structure, the asymmetric structure which forms around the particle, and the particle moves with that. That's what is shown here. So as you see here, starting from very early time t equal to 0. So at t equal to 0, the position we record it to be at, position equal to 0, the coordinate 0, because it starts from there. Initially, you see it moves into the negative x direction. Yeah, so it moves into one direction. Beyond a certain time, it suddenly changes the direction, and then it finally moves to the positive x direction. So it means that it has now completely changed the direction of its motion. And that is something very interesting, that why does it change the direction of its motion at all? So these are some of the things which are of extreme importance in the context of active matter. If you have already come across this term, so there is something called active matter, where people look at this kind of motion of particles. It can happen under different situations. It can happen under the gradient of temperature. It can happen under the gradient of concentration fields, chemical potential gradient, or some kind of electric field, etc. So there are different terms which are associated with it, like thermophoresis, chemophoresis, diffusophoresis, etc. So those are some of the very active topics at the moment in the literature. And this kind of motion of particles, the properties of this type of motion, these are of extreme importance in the study of such active motion. Okay. So now to explain to you about the motion of the particle, I kept this slide basically. Let's not get into the detail. What I show you here is plot of the velocity of the particle, which is undergoing motion. So y-axis is the velocity, x-axis is the temperature gradient. Okay. The left one is for a philic particle, which means that if I take this Janus particle, both the right and the left side, they prefer water phase. The right one is for a phobic philic colloid, what means that the right part, the cap part, does not like water and the left part likes water. Okay. So if you look at the velocity here, first of all, let's have a look at the philic case. You see that when the temperature gradient is small, the velocity is small. As the temperature gradient increases, so as you move towards the left-hand side, the velocity also increases. And that is something which is expected, okay? Because if you look at the mechanism behind this motion of the particle, it happens because of the temperature gradient. The moment you have a temperature gradient, you have a concentration gradient around the particle. Why the concentration gradient? I already explained to you before, right? Because you have these structures which are forming, and depending on the local temperature, the local concentration is going to be different. And both sides of the colloid have different temperatures, which mean that the concentration is going to be different on both sides. So you are going to have a concentration gradient. So the higher the temperature gradient, the stronger the concentration gradient. And when you have a concentration gradient, that leads to the motion of the particles. Why so? Because it's basically like the higher concentration means it's like higher pressure. Okay, so if you look at the solvent molecules, they will try to move from the high pressure region to the low pressure region, and the particle will then move in the opposite direction. Okay, so that's the basic mechanism behind the motion of this type of particles. So when you have the lower temperature gradient, velocity is lower. As you increase the gradient, velocity increasing. As simple as that. That's what you see for the philic case. What is very interesting is if you look at it for the phobic case, because here you see up to a certain temperature gradient, the velocity is negative. It's less than 0. Yeah. And then beyond a certain temperature gradient, the velocity has now crossed over to a positive value. So what does it mean? It means that if my Janus colloidal particle was initially moving in the right-hand direction, suddenly it has changed the direction and it starts to move in towards the left-hand direction. Okay. And that's what I mean by the change in the direction of motion. So this is something, once again, of extreme deep importance, physical significance, and it's very interesting. And there are works where people try to characterize the direction of the motion, in which direction the particle should move, depending on its surface properties. When can it change its direction? How can you tune the velocity of these particles? How can you tune the direction of its motion? So on and so forth. It's a very active topic of work where people are doing a lot of research trying to understand this kind of motion, trying to find the answers to this type of motion. All right, so with that, basically, I'll end today's lecture.